Okay, so just a few things. Yeah, I was not alone doing that. We have quite a few people doing that. We have Carl that managed to get boards from China in less than a month. Got boards made, custom boards. Yeah, all the other people for testing, rating, and all of that. So yeah, just some ground rules. Don't be a dick. That should be enough. And try to not touch other people's computers if they did not let you touch them. And especially with the boards, because yeah, that happened to me once that someone took a board from my computer that was an interface with high voltage and USB and just put it on the screwdriver, and that just shorted the thing. Yeah, so just avoid that. Purpose of the class, I'm not here to teach you Verilog, to teach you all the intricacies of flip-flops and all of that. That's not the purpose at all. The purpose is to get you started with a board. So being able to just get it working on your computer, getting all the tools set up, how to do basic examples, and just get started. And then you can learn on your own the language and all of that. Because it takes a lot more than a single class to learn all the logic, all the commands, all the specificities. And that's usually too much in a class, so people just get lost after the first lesson. Okay, so you will get a few things. You will get that Colorlite board, which is the FPGA board on itself. It has a flash on it, and it has 2 Ethernet PHY. So that's what's going to allow you to have Ethernet on these. That's a SODIMM factor. So that's a thing that this Muse lab in China is using more and more. So they do a bunch of other FPGA boards. So that's coming from a company that makes LED panel controls. And people have just reused this SODIMM factor and just use it for other FPGAs now. You will get a support board. So that's the other board that, yeah, I can show that. You will get a support board, and everything will be mounted already on it. So try to not play too much with the SODIMM, because they are not made to be inserted and removed too many times. So you just be careful with that. And the contacts of the JTAG programmer, which are at the bottom, are not extremely good. So you may have some issues if you do that and don't press it back well enough. So what this board does is give you an HDMI, gives you USB. So the USB is not connected directly to the FPGA. It's connected to a programmer, and it's connected to the serial lines of the FPGA. So you can program it, you can talk to it with serial, you can power it, but you will not have the USB connected directly to the FPGA. Then you have all the PMOD ports on the sides. You will see that we populated for you the 2 on the sides, but we did not populate, especially the ones next to the HDMI. Don't populate them before you're sure that you have a cable that fits in between, because they get in the way and you don't want to have to desolder a full connector once you've done that. Okay, and then we have the...
So the USB hooks to your computer, and that's a JTAG to the FPGA? The USB connects to your computer, and there's a JTAG program?
Yes, and below that there is an STM microcontroller that does the programming and all of that. And it acts as a DAP link, traditional DAP link thing. And then you will get the Ethernet board. So that's the one that Carl made. Well, ask a Chinese company to make it, and yeah. So he asked someone else to do it. Well, thanks, Bob. So it's just pulse transformers, because the PHY are already on the SODIMM module, so it's just pulse transformers and the Ethernet part, and some capacitors for fun. Okay, any question so far? Nothing? Okay, I was going to do a basic reminder on logic gates and flip-flops and all of that, and decided not to. So unless you really want to learn about that, and we can go case by case, you're not going to need that anyway for the examples we are going to do. So I think I will just keep on that. The only thing I wanted to talk about maybe at some point is about the propagation delays, which is something really important in FPGAs. And yeah, so I will not get in the technical details, but that's the important part of how fast can your design go, and can it even work? Okay, so we're ready to start. We can distribute the boards. So you will see, you will copy and paste code. You don't know what it's doing. Doesn't matter. Okay, we will go through it. I will explain what the things are and why you want to do them.
Take one and pass them down, or just slap them? See how this works. Okay.
So I recommend you go to the website, so you have it on your computer at the same time. That way you can copy and paste and not type stuff. I hope you all have the address. I can give it back if you don't have it. Yeah, and you go to Listen 1 in it. On the website, I also made a section called Candy Jar, where you have more advanced explanations of things. They may be completely wrong too, because we did not have time to review them. But yeah, that's more advanced explanations. Okay, another thing with these boards, I mean, if you played with microcontrollers before, they tend to be a bit more sensitive to what you do to them. So be careful. They are 3.3 volt. So don't connect 5 volt stuff on them. They will really not like it. And the fun part is that usually you don't fry the FPGA, you just fry the input-output. So the FPGA still works, but doesn't output what you want.
Does it matter which side I go?
Yes.
So the die reads the right way? Oh, there's using
J1,
there's
yeah.
pin out.
Yep. And that's the way it goes.
Okay, yeah.
So J1 goes to P1.
Are we going to plug it in, or?
Yeah, you can plug it in. And you can plug it in. It's going to use its default program, whatever it is on it. Just another thing. So FPGAs, they are programmable components, right? So it's not like a microcontroller where you have a CPU that's going to execute instructions and all of that. What it is that it's a bunch of really basic functions like flip-flops and adders, multipliers, and sometimes really fancy DSP stuff. And what the whole suite of programs is going to do is decide how to connect these things together to make the design you made work. So the FPGAs are reprogrammable, which means that this routing can change anytime you want. So when you power the board, yeah.
Sorry guys.
So when you power the board, it has nothing, and it's going to try to read from a flash its routing information. Okay. So what happens when you program the way we are going to program today? We are just going to tell the FPGA, just wipe yourself and get that routing set up. If you unplug it, it will lose the program. Okay. If you are interested, I have added instructions on how to program the flash. And then you can program that flash with your settings, and it will just, anytime you plug the board, it will reuse your program. Okay? Okay, so we are going to make one of the most basic things you can do on an FPGA, which is to blink an LED. So you will see on your board, you have two LEDs. When you plugged it, you have a red one, which is always on. You don't have control on it. And next to it, there is a tiny green one, and that's the one you will be able to control. Yeah, you will only see it when you plug it in. Okay? Okay, so how does that work? When you work with FPGAs, you are not working with programs. It's not instruction that you are telling it. You are not telling it, you light the LED, you wait, and then you turn the LED off. What you are working with is signals. And you have to say, there is a signal coming in, what do I do when the signal looks like that? In what state am I? And then what do I do next? Okay? So that's Verilog. That's one of the many languages that exist for FPGAs. That's a major one in the US. In Europe, people use something else called VHDL, which was made by DoD, I think, which is a fun thing. But VHDL is more complicated, and it's more rigid and rigorous, but it's also more complicated. So yeah, we go with Verilog. So that's the structure of a module. So anything in FPGAs is made with modules that you connect together. So instead of making one giant program, you just reuse modules, and you will see, I will give you links to something called open cores, where you can get a module that does serial and get a module that does HDMI and all of that. So you don't have to do them. You just plug them in your design, give them what they want, get what they give out, and use that. So it's really a puzzle approach where you connect things together. So what we have here is that we have a module that gets a clock in input. So that's an arbitrary name. So it gets an input, and it gives an output. And what we want to do is to make it blink. So we want to take that clock. The clock on your board is 25 megahertz, which is really fast for something to blink. So what we have to do is to what we call divide that clock. So we are going to make it slower. So we are going to call a module that we are not going to talk about that takes a clock and slow it down by a given ratio. So here we are slowing it down by 200,000. And you can change that, and you can change that value. It's basically going to wait for 200,000 positive edges before switching, and then do the next thing. So that's how it slows down your clock. You have ways to make faster clocks too. So you can have faster clocks than the 25 megahertz, much faster clocks, which is also one really useful thing with FPGAs, but we are not going to use that. The project we are going to use with the Ethernet is doing that, but it's doing that for us. So we are not touching anything for that. Okay, then we talk about registers and wires. Registers are like memory places, so it's a bit or wider. So it's just some place where you store values. Depending on what your program is, what you want to do with it, what your FPGA is, what the suite you use, it's going to manage that differently. In some cases, it may optimize it and use its own kind of memory to reduce the load on the surface of the FPGA used by your design. So I'm talking about surface. I told you FPGAs have a lot of primitives on them. They have a lot of gates, and they have flip-flops, and they have what we call lookup tables, which I will talk a bit more about that later, but it's given inputs, what will the output be? Okay, and that's a basic of almost everything in an FPGA is you are just programming these lookup tables, and that's what's going to make all your logic and all your signals go together. Same thing, we're not going into the details today, but that's what happened inside. And it takes space on your FPGA. So yeah, I want to show you that. And if you go to the candy jar, and you go to ECP5 in detail. So the ECP5 is the FPGA you have. And that's what...
The FPGA what?
That's the kind of FPGA you have on your board. So they have different models. You have the most basic one. And that's a representation of your FPGA. And all of these tiny... So on the outside are all the input-outputs. And all these tiny blocks, it's a combination of lookup tables, adders, multipliers, DSPs, all kind of things. Okay? And the purpose of your design and all the software we are going to use is to decide, okay, they want me to blink that LED, so I need to divide the clock. So it's going to decide to divide the clock, I'm going to use this module and connect them that way and all of that. Okay? So it's going to take space on your device. Physical space. So the divider will be here, and the blinking part will be here, for example. Okay, so that's why we talk about surface area used on the chip, because it's physically taking some space on your chip. So if you, yeah, you can look into, and I give you the, so you have what they call PFU blocks, and these PFU blocks are divided in slices, and each slice has lookup tables, registers, RAM, ROM, multipliers, adders. Okay, and that's what you get when you do the blinking program. Okay, that's what the software is going to do. Is going to tell the FPGA, you connect that thing to that thing, you connect that thing to that thing, and that's what makes it work. So it gets the clock, does all its magic, and that's the LED out. And that's a software that's included. I'm not going to show it because it uses Qt and it doesn't work on every platform, but the place and route program that we use has a GUI option that lets you see what's happening, and you can follow and click on the wires and see what they do and all of that. Any question? And you can stop me anytime if I use words you don't know or don't understand. We all come from different backgrounds. We don't know the same things and all of that. So don't hesitate to just stop me. Okay, so we have this register. So you just think of it as a store of value. Okay, so we are going, and it's a single register, so we are just going to store a bit there, 0 or 1. We have a wire. A wire is just a way to tell in your design, I want to connect that thing to that thing. And that's a name I give to that wire. Here we are talking about the clock divider. We are giving it a parameter called div and giving it the value of 200,000. We are giving it a name, giving it inputs and outputs. Okay, so it's going to take that clock I that we use here and generate something called base clock. And if you look below, that's a definition of the clock divider module. And it has a parameter we are talking about, and it has an input wire and an output wire. And it will divide the clock for you. But you will copy and paste it, you can see that code, you will see what it does. But I'm not going to explain it because it's, for a blinky thing, it's a bit too much. Then we talk about the real logic, so what's happening and when in your design. And that's where all the problems in FPGA happens, is when you have to make sure things happen in the right order, and they have to happen, not just in the right order, but also with the right speed and the right signal at the right time. So the difficulty is not that much about writing the code, it's more about making sure that whatever is going to happen after is going to make the design you want to make. So most of the work on FPGAs is about simulating, testing, and calculating your clocks to make sure that things can happen in the time you say it's going to happen. Okay? Because I was talking about flip-flops, they take time. It takes time for a signal to enter something, to be stable enough for the output to be stable as well. So if you have one, it's fast and it works. If you put many next to each other, you start to have delays that build up. And if you have more delays that happen than the length of your pulse, to simplify, you're out, and you cannot make things happen.
You have more delays than what?
So yeah, if you have a pulse, right? A pulse for your clock. Yeah, so it's low and then it's up. When it's up, what's going to happen is you need a little bit of time before that and a little bit of time after the positive edge of your clock for things to settle down and be stable. And now I'm going to add another flip-flop that also needs to be stable for some time. So it's going to be added after the other one. And then I add another one. And at some point, I'm reaching the negative edge of the pulse. And that means I cannot do anything anymore because I don't have that clock happening.
Do you have to keep track of the rise and fall times and the settlement times, or and can you adjust that?
Not really. So the rise and it's not really rise and fall. It's settling times for your, and it depends on which module you are talking about. So lookup tables will have a different timings and the flip flops and the adders and all of that. So your design tool will know what it is. Will do the calculations for you most of the time. I mean, in practice, I'm sure you have weird stuff happening, but yeah, it will keep track of it and it will tell you, hey, you asked me to have a clock of 100 megahertz, but I don't have the time to do that. So what you have to do in that case, you have to break down your design in multiple parts that are not dependent from each other and make sure that it works. For this example, it's fine. If you look when we build lesson 3 with the Ethernet, you will see that at some point it's telling you, hey, you asked me for a clock of that value, I cannot reach that. It still works, but your design is not optimal and may fail when you use it. So it's warning you, it's calculating things for you, but you still have to be careful about that. Okay, so here we are telling it, every time you get a positive edge on the base clock, so the one that we generated with the clock divider, you are going to invert, so that is tilt sign here. You are going to take the value of LED register and invert it and put it back in LED register. So if LED register was 0, which it is on this kind of FPGA, when you start them, it will be 0. And the next clock, it will be 1, and the next clock, it will be 0. Next one. Okay? Like that. Depending on the FPGAs, it's not always 0. Some FPGAs, they just start with random values in the registers. Some other, these, you can also tell what the value is. So it's not all FPGA can do that, but you have a kind of block you can put and say, at the beginning of my design, when everything gets started, that's the values I want inside the registers. So you can do it, but it takes special setting. Does that make sense for everybody? But are you set up with your computer? Yeah, okay. Okay, so we have a register. This register is going at 25 megahertz divided by 200,000. So you can do the math. And it's going up and down, but you don't have any way to see that. So now what you need to do is to take that register and associate it with something on the outside. And that's what we do with the assigned LED O to LED register. And that's going to happen. It's always going to make sure that this register is assigned to the LED here. Make sense? So what happens really in your FPGA is that at each kind of clock domain, so we call them clock domain, at each clock domain in your design, it's going to run things in a specific order. So it's first going to do some kind of assignments, and then the other kind of assignment, and then do the physical assignment from the register to the GPIOs. And that's where things can go wrong, because you can tell it to do, I have the details in the candy jar, but you can do two main kind of assignments, blocking and non-blocking. And you have some that will happen at the same time, and you have some that will happen one after the other. So you write them at always positive edge, and you make 3 values. And if you put the blocking one, they are all going to run at once. If you put the non-blocking ones, they are going to run, your value is going to jump from the first clock, and then the second clock, and then the third clock, if you have 3 conditions in there. So same thing, that's more complex stuff, but that's something you need to be really careful about. And it will hit you when you design things. So I explained that same thing in the candy jar. I have an explanation of these assignments. For this kind of thing, we are doing only a single one. It doesn't matter. It does not change anything. So you could use the one with a lower than sign or not, which is a blocking and unblocking. It's not going to change anything. Okay, make sense? So you're going to take that. You're going to put that inside a text file. And that's a representation of what's happening, right? You have your module. We always call it top. That's the base of your design. That's where everything is going to start from. It's getting a clock as input, and it's changing the GPIO as output. Okay, so we looked into some details of what's happening there. So yeah, you just make that file, or you copy it from the GitHub repo. You just choose what you want to do.
Is there a recommended file name extension really? No
Blinky.v.
.v?
Yeah, extension is .v. I don't think it matters. The tool will take whatever you give it, but
That's the convention.
yeah,
Oh, I see.
Save it in the projects folder and like strengthen.
yeah, anywhere you want. Make sure that you have activated the environment, like we have done. Yeah, let me show that again. So for Linux people,
We put it anywhere? the text box?
yeah, you put it anywhere. For Linux people, remember that you have to activate the environment before using anything. On Windows, it's the same thing. You just have to activate it in a different way. And in your terminal, it will tell you OSS cat suite at the beginning of your prompt in most of the distributions. So you know that you have activated it. And just let me know if you have an issue with that. This is what we want to happen, right? We want this LED to blink by a clock that's divided. And we are not talking about gates, we're not talking about anything, but we will need tools that will take that design and try to apply it to your FPGA. Is anybody stuck on getting the environment up or anything?
microphone.
Yeah.
But oh well.
So we're supposed to be pasting the LPF stuff into a blink.lpf and putting it in
Yes.
the same folder as the source.
Yes.
.lpf?
Yes. Same thing, it doesn't really matter because you're going to give the name of the files to the tools. But I think it's a good convention to have.
Makes it easy to carry.
Okay, so that's, oh, wrong screen. That's what we know so far. Okay, we have a clock. We have a clock incoming. We have some magic that divides the clock. We have a base clock coming out. We are waiting for a positive edge of the base clock, and we are just inverting the LED. So that's the design we have.
There was one thing I wanted to mention. You said you could put clocks into any pins, but actually there's certain pins you could only put clocks into.
Well, yeah, it depends if you design. Yeah,
Yeah.
depend on the speed of the
It's
clocks.
in that,
Yeah,
CSV file you have,
Yeah.
like, it tells you which are.
yeah, you have clocks and clocks, but yeah,
Yeah, because usually in an FPGA you have this clock tree
yes,
that
Yeah.
feeds all your flip-flops, and you have your data, and they want you to keep it separate. And like even the Xilinx tools will error out when you try to cross the path, cross the streams. And you can reduce it to a warning by like telling you, hey, I actually want to do this, but yeah, type of thing not supposed to.
Yeah.
If you want like very tight timing.
yes.
Yeah.
So that's the thing. There are a lot of magic happening in these tools. And that's why we use these open source tools, because people have reverse engineered most of the commercial tools for these kind of FPGAs and a few others to understand what's happening, how the design is made, what do you see, how do you need to generate the program you're going to do put on your FPGA. So that's the interesting part, because nobody saw that before. It was just a commercial company that was making a black box, and you will put your design and they will generate the things, and you put that on your FPGA. And now we have tools where we can start digging and seeing what happens and what you could do differently, and what happened in a specific chip, because each FPGA is different as well. So as he was saying, you have things that are forbidden in the design of some FPGAs. So there are things you cannot do. So the tools need to know that these things, you cannot connect them together because they cannot be connected together. Or if they are connected together, you have a really slow link between them. So it will add a lot of delay. Okay, so everybody's ready? Okay, so we have steps. We started with a Verilog file. We are going to use a synthesis tool. Am I on the right? We're going to use a synthesis tool called Yosis, which I think is moving, which is going to generate an optimized design for. So it's going to try to take all the bits you made and try to design the low-level components to make that design happen. Then it's going to map it. So it's going to map it to the specific FPGA chip you have. So it knows that you try to do a multiplication. Hey, guess what? I know that your FPGAs can do multiplication with specific modules. So I'm going to use that specific module instead of creating a whole tree of gates to do multiplications. So in the case of the FPGA you have on that board, there are DSP modules, for example, to do digital signal processing. And the open source tools don't know how to use them yet. So for example, it's not going to automatically map to this, so they stay unused for now with the open source tools. Then you have the place and route. So you remember I showed you the diagram of the chip with all the tiny modules on them. And that's the tool that's going to place things next to each other if they need to be next to each other, and far away if they need to be far away, and connect them together. So on a simple example, it's fast. You will see you're going to run the tools. It's going to take a few seconds. On Xilinx, even for really simple examples, it's much, much slower. Now if you have complex designs, it can take hours. On really big FPGAs, it's going to take a really, really long time to do the full part of the place and route. Because it has to try things and make sure that they can work together and realize that they don't break everything down and start again. So they have really advanced algorithms to do that, which the open source tools don't always have. But yeah, that's one of the most complicated things. And when you run the ALSCOP project, most of the time was spent doing that, trying to find space for the Ethernet and all the other modules in the example. Once you have that, you know what you want to connect to where. We are going to have a tool that takes that and is going to generate the binary file that's going to get inside your chip and tell what is connected to what. And same thing, people had to reverse engineer that and understand what that format does. And that's a lot of magic for that too. Okay. So that's what you're going to do. You are going to run these steps manually. You're going to generate the design and the mapping with your sys. So you're telling it, hey, I want to synthesize from ECP5 FPGA, which is a kind of FPGA you have. The top module is called top. Same thing, I recommend that you use top for your top module. You don't have to. You can tell your tool to use something else, especially when you want to test and things like that. But yeah, as a good practice, just keep that. You're going to ask it to generate a JSON file that will contain all the description of the design from the blink.v. So you change that name if you use something else, but that's your Verilog design description.
Oh, so we should do that?
Yes. So run. Yeah. Yes. So blink v input, blink JSON output. Run them one by one so you can see that things are happening and the kind of output you get. If you look in the class GitHub, I also made make files that will do the thing automatically. I think for the class it's better to do it manually. We don't have a lot of things, so it's easier for you to understand. But later you can use these make files to automate a bit all of that. So it will rebuild automatically when you change a V file and do all of that. And again, it's a good thing to see things breaking. If you did a mistake when you copied and paste or changed something, it's a good thing to see what was wrong with your Verilog before trying to run something else.
Oh, do all three of those?
Yeah, you run all of them, and I recommend you run them one by one so you can start to have a look at the amount of information that each of them is going to give you. That's a lot of information. It all makes sense. It's all extremely useful when you design. You're never going to need everything for every project you do, but when you have a problem, that's where you're going to see why you have a problem. Maybe because it did some assumptions from what you wrote in the Verilog, and that's not what you assumed it will do. And there are some edge cases where when you do your design for one kind of FPGA with the same Verilog, you will get something completely different on another kind of FPGA. So you need to also be careful on how things are interpreted. I was talking about that, for example, for initialization of values. On these, the registers are initialized at 0, and you can initialize them to something else. On others, they are just random, and you just have whatever is there. On Xilinx, I think by default they are 0, and I'm not sure you can initialize them. On the Xilinx, I'm not sure you can initialize them to something else without making your own setup groups and all of that.
Yeah, you mean initializing
The registers, yeah.
I think you could just, on the later Xilinx tools, you could do equals. Like when you define a register or a wire, like you could, or a register, you could do equals 1 or 0
Okay.
or IC. Or you could put in an initial block.
So this work on Xilinx too? Okay.
You
Yeah.
can use an initial block. The whole issue with resets and power on resets.
Yes, yes. So yeah, that's another thing
That's a
is,
huge mess.
yes. So what happens when you reset your module, what it should do? Most of the FPGAs, the good thing is that they block all the output, all the IOs in high impedance mode when you restart them. So at least you're not frying things when you connect them. I don't know if they all do that, but at least this one does. So you're sure that whatever is connected will be safe until you. Now, if you upload something that acts as an input and it goes to another output, then you have problems. So you need to make sure that what you connect to your board corresponds to what design you are sending to it. And I'm going to insist on that. It's not because you described it that it's going to do what you described it to do. And that's something I'm not going to talk about today, but you can also in Verilog and VHDL write testing suites, like test benches, where you say, I want, when I do that signal as input, I want this to happen. And it's going to use the clocks calculated from your design and see, is that really what happens?
Does Yosis or does all of this open source have
Yes.
tools to do this?
I think it does, yes. I've not used it yet, but I think it does.
Yeah, 'cause I'm used to using some type of mental graphics thing where I can like draw signals and like debug within just the before doing the routing.
Yeah, so in that case, yes, and you have also simulators. So you can even run, we will talk about system on chip and all of that, but you can even run the system on chip on the simulator. So you can have full CPUs emulated and test that. And that's a good thing with the LiteX and all these open source tools, is that they manage to get everything working even if you don't have a board. So you can do all your design in your computer and then push that to your board and test it. And yeah, I'm just going to talk really quickly about that, but you use the same tools the same basic tools, not the latest one, but to generate designs for ASICs. So if you want to generate your own custom chip that's really fast, does not suck up too much power, and does one specific thing really well, you can design it in Verilog, and then the mapping and design is going to be completely different. All the problems after are completely different. And Carl can talk more about some initiatives that exist where you can have open source designs made for you on ASICs. So I have, in the presentation, I gave some links on these different initiatives, so you can have a look at that. And they explain how things work and how you can submit designs and what happened as horror stories on the designs and all of that. It's all pretty cool.
Now I'm also noticing I'm running into a problem with actually programming it to the board.
Okay.
ECP Oh wait,
It's working.
I ran
Yep.
it the first time and there was an error.
Yeah.
The second time, okay.
Yeah, it takes some time for the microcontroller to boot up.
Okay.
Okay. And it's blinking.
Are we supposed to be trying to run it?
It's blinking really fast, but it's blinking.
Yeah.
Okay, so who did not get it blinking?
Nobody told me to make it work. No probes found.
Yours is blinking really fast.
Yes, by default, it's blinking extremely fast. And that's part of the exercise where you have to make it blink slower.
Mine was blinking a lot slower.
I got an error.
So that's yeah, no, I had the same problem on Linux, is that
The pogo pins.
Maybe.
yeah,
That's like the first thing I'm going to try.
yeah, because the version of ACP DAP I had was not working in LSSCAD on Linux, on Fedora. But it was working on Ubuntu, so yeah. Oh, it is doing things. Wait, why is it blinking like that?
See, why isn't yours blinking at that? Yours is blinking really fast. Then you got rid of a 0.
I didn't touch the code.
Yeah, so
Maybe it's not really working.
you're going to... You did all the groups stuff and all of that, right?
That looks more to me like a USB.
Type groups,
Yeah, but this looks like a USB data.
plug dev, dial out. Yeah, so you're good for that. So I think it's the ECP DAP that's wrong. I have other... If you click here.
Let me ask. This looks like USB data. Is that?
No.
That is not.
No, it's blinking.
There you go.
Just fast.
It's really fast. It's blinking really fast.
Cable.
I don't think it's a board. I really think it's ECP DAP that's failing.
Versus, yeah, there's
Okay,
the
try it.
versus what's on the webpage.
Yeah, I copied it from the web.
Hey, look at that.
Yep. Tell you.
I guess, yeah, you increase the...
So,
Let me.
in that case, we have other instructions that use another programmer that works better.
Sure, so I might not have ever logged out in any game.
No, you are in the groups. It's not. So it's ECP DAP that.
It doesn't tell you you've logged out.
No, that's fine. If you are in the groups, it means that you are fine. Yeah. Yeah, you are in the group, so you can
Logged out.
Oh,
do
Log
do
out in
ECP
again.
DAP space probes.
are you? Is it not talking to the thing? Like,
Hang
is
on,
this
hang on.
is this an emulated serial port?
No, it's an HID. It's its own thing, and the problem is that on Linux, the ECP DAP that they shipped in your SSCAD is not compiled properly. There is something wrong with the USB libs.
Well, it
So
wants you to be in the dial-out group, which usually means that you're emulating a USB. Or you're emulating an RS-232.
yes, after there is a serial port when you use the LiteX later. So that's why I wanted
Because
both.
I couldn't. The script did not do that. It did plug dead, but it didn't. It did not succeed in
I noticed something like that
setting
too.
that.
Try the other one.
And I wonder if maybe
So,
they
yeah.
changed it or deprecated it.
Go down. Try that one.
Is there another one?
Yeah, that's another programmer. Remove the sudo.
So this isn't. This doesn't just start up with the. Oh, it didn't.
What the hell? Oh, sorry. Go up. Remove all of that. Just call open FPGA loader. What the hell? Did you do the UDEF rules?
Yes.
Did you restart them?
Hang on. So I just realized another thing. I was testing all this on Debian, another box. So who knows what I've done on this?
Yeah, it looks like you don't have the UDEF stuff, but
So this board is
That's in the script.
this board is defective.
why?
So slow the LED lights.
Huh?
I changed it to butter.
Yeah, that's good.
But not right now.
It's cool. I love FPGAs.
Well, it blinks. Yeah.
You know, it was an amazing concept for me to like figure out in the beginning. Is you write all this code and then you can instantiate as many times as you want. Nothing
Yeah.
slows down.
Yep.
It's like nothing
Well,
slows.
as
It's
long as
all
you-
running in parallel.
As long as you have space,
Yeah.
you can. Yeah.
Dude, like a lot of code.
Yeah.
No problem.
What?
Yeah, it takes some change of mind.
yeah,
If you did programming before, you have some
You're
things
thinking
to.
about things are serially
yeah.
done and they're not.
Good. You're blinking.
You can go to somebody else.
Hmm?
I'll get it.
One error. You don't have the LPF file.
Say again?
You don't have the LPF file. That's the other file in the lesson. Yeah, you're missing one file from the lesson. Go back in your web browser. Go up. No, go down. That. You need that file, .lpf. Are you blinking?
Yeah, I modified it to go a lot slower.
Okay.
And Copying and pasting all this stuff is for the birds, so I'm making a shell script just
Okay. Yeah, and if you look in the Git repo, there is a make file that does everything.
Yeah, but it's like I actually changed the name of the file just so that it forced me to like go in and fix everything.
It's asking for a shared library.
Yeah, so remove the sudo and remove the path. And just call open FPGA loader. Because ECP-DAP did not work.
Remove the entire path?
Yeah, you just keep open FPGA loader. No, remove everything except open FPGA loader.
I have to point to it though, it's not in that directory right now. But you have the environment set up so it
Yeah,
knows where
so
everything is.
do that. Yeah, okay.
Okay, so yeah, because it's just easier than it's the SVF. The script set up all the paths to all your tools. So all your
But
tools
did you do the ECP-DAP?
Try the ECP-DAP first. I don't have that on my machine, I guess.
No, it is. It is installed in SSCAD too.
I didn't do it in here.
Yeah, the open FPGA loader one is just in case ECP-DAP doesn't work, which it. Ooh. Yeah. Okay. So that's. Try again. Do you hear that click?
Yeah, I heard the click. Yeah, I heard it click. Yeah, it's the these pogo pins.
So when you see errors about chains like that, it's because it's not able to get all the bits right.
Good thing we
But
ran into that
it
problem.
means that it's able to talk to it.
Yeah. Good thing we ran into that problem. But did you hear the click? I heard the click.
Okay.
Yeah, you're good. Is it blinking so fast? Yeah. It's set
Yeah,
to
it's blinking.
200. You change it to
Hey.
Hi.
So blinking fast.
Maybe it says it claims to have programmed it, but it's not blinking.
No, it is blinking. If you move your eyes.
Really tired?
Okay, it's blinking.
Yeah, it's blinking, but really fast. That's it. And that's part of the exercise, is to make it blink slower. Yeah, blinky.
The first part's like, so far I'm like following everything you're saying. Once it gets like into the LiteX stuff, that's where I'm like, okay.
Yeah, and again, I'm not going to get into the details of. Yeah, that's a lot.
Beyond what you can
Yeah. Okay, back program. It works.
I was told there would be no math.
So we started here with, what is it? 200,000.
Works. That works.
You got it running there?
I'm telling you, this ECP-DAP is broken. On my Fedora, I had to install ECP-DAP myself.
So you probably weren't here.
I don't know what. I compiled it with the wrong USB version.
Configuration into the FPGA, and it powers off.
Yes,
It's gone.
I just
Yes.
discovered that.
Yes.
So
How do you burn it in?
You have a flash?
That's another lesson. Right. Got it. Got it.
Yeah.
You actually burn it
No.
externally to it.
If you do ECP-DAP flash blink bit, it will do
yeah,
it.
do ECP-DAP flash instead of program.
Go off script. Go rogue.
Yeah. I mean, that's the purpose of the class. It's break things, try things, and make it crash,
I
burn.
protected all the flash.
Did you mute?
No.
Okay, good.
Oh, it's SVF file, right?
Hmm?
You have to flash the SVF file.
ECP-DAP, you have to flash
It's the SVF file, I thought, right?
the bit file.
Is it the bit file?
Yeah, it's a bit file.
ECP-DAT flash.
So it's a bit, yeah, it's not. Go to Canija. Yeah, and that's, yeah, the command is a bit more convoluted than that. Flashing and programming the ECP5. Go down.
That means there's a man.
Probably because the,
Ah,
further,
I forgot to.
you have to use another.
Yeah, let me check. I don't remember the exact command for it.
I probably want the other one. Give the second one a different one. Yeah, cascade it. So it's sure.
ECP-DAP flash space right space.
Oh, it's right. That's right. Slash right. Then the bit file. Bit file?
Yeah, bit file. Yeah, the SVF is.
It's
It's
an
just a.
extra word.
yeah.
Flash, but then it's right.
bits.
And then it's the bit file.
So clocking is
After it's inside the command
You have
of
to do a
Flash.
help on the Flash command to see.
It's a subcommand of Flash. Because you can do a Flash ID and a Flash scan to know if you have.
you change that to 1. And then the input would be base clock. And the output.
You unlocked all of them, right?
Yeah, all the ones that I had, like
Okay.
like Andrew's I didn't do, yours I didn't do,
Okay.
Peter's I didn't do.
You just reinstalled?
So,
And reboot.
once again, I may not have ever installed.
Yeah, okay, so it was the UDEV rules. Okay.
It should be 20, whatever that, because this is not going to do it.
I don't think it's the reason that it hung during the middle of the install, but I added a third term at the top, Linux Mint, because it's like supposed to be just like Ubuntu.
We haven't seen your pull request yet.
What? No, at the install script.
Redux.
SPI flash read.
Man, unprotect
Ooh,
on
I
everything.
didn't like that. Was it for the wrong device? Or did I type it wrong?
Maybe.
We're not supposed to know that.
Yeah, it's documented on the website.
Do you have to do it before every?
No, I think it's unlocked.
You think so?
Could you put it on the same thing?
I never tested it.
Yeah, I thought I tested that.
Could you
Okay. Well, good to know.
I'm gonna use him as a test case.
Yeah.
I'm gonna unplug his board.
Yeah.
I'm gonna do it.
Wow, this is like.
Or maybe
good.
it doesn't. The unprotect doesn't take until you write it right after it. That's a process.
Maybe, yeah, that's, yeah.
Imagine a lot of this is boiler.
Because I didn't write anything.
Yeah, that worked.
I just unprotect.
Okay.
Like,
Why is it not blinking? Yeah.
Oh, because I think you have to reboot it.
you have to reset it to make it go.
Is your program already blinking? Oh, you flashed the SVF file. Yeah, that's not going to work. You're flashing it a file that it doesn't know about.
Wow, that means it'll just burn what you tell it to.
Oh yes, it's not going to check anything. It doesn't know, it cannot
You
know.
could burn a JPEG. in
Yes, absolutely. You cannot read it back.
Clock is just flipping
I mean, you will have to read the flash manually, right?
You've heard of bricking things, right? We're supposed to be able to play that without.
Yeah, there we go. So unplug that board and plug it back.
do
Do you mind if I use your setup really quick as a test case?
Can you unplug the board? So I'm going to add that in the instructions on the website. I had the unprotect already, but
Paste this into a little scratch pad that I've got.
I forgot that wasn't on the website. I had to help it figure that out myself.
Okay, and if I do this, Control V, then I have a record of what you just told me to do, and if I save it, then I'll have it, and then I'll come back to it, and you want that.
No, you can stay. Like, I'm just gonna power cycle.
Nothing. I added a power cycle in between.
And we would have the donuts measure the.
Why do you keep giving this shit?
Yeah, it finished. So it's possible.
So if I power cycle it now,
because it's 2.
Yeah. I mean, it's all good. I just wanted to.
no, I hadn't done that, so, if we're really putting this.
Charge the upload its data to AWS. And once it's charged, click it back out. So for a picture long term, that's obviously not going to work. So we did it.
okay. Yeah, I updated it.
And we put a solar panel.
Okay.
Battery it would basically charge.
Okay.
So start the next step.
Do you got it to work? Yeah.
Yeah, yeah.
Okay, so we are going to go to the next one now. Do you need help getting stuff?
He's gonna game.
Okay, so we are going to the next one. I need you had cables
Yeah,
in your
yeah, I
hand.
had 'em, I had 'em.
So now we are going to use inputs. So we had outputs. We had an input which was a clock, but now we are going to have a program that reads whatever you put in and outputs it to the LED in a weird way.
Do you need one?
Yeah, fine.
Don't cut it. Never.
Okay, so just a tiny thing about GPIOs. That's the same pin that I knew that would happen. So the same pin can do input and output, and you have systems inside. So Andrew made a video recently about that. I sent it to you by email. We'll add it on the website. But the same pin can do input and output. And you have a system that switches between the two. And each input can have different modes. So it can be open, which means it's at whatever high impedance your chip can do. Or you can also pull it up, which means that you are going to apply with a resistor that is inside your FPGA chip. You have a resistor that's going to put your input as a high value, high voltage. And anytime you're going to put it to ground, it's going to become 0. So by default it's 1, and it's going to become 0. Or you can put it down, where it's going to put it at 0, and you will have to put a voltage to put it up. So why we need to do that is because if you don't connect anything, it could be any value. It could be up, down. It's going to have a voltage just by charge on the pin. So you could have a random value read. So that's why we always pull things up and down to avoid these kind of issues. Make sense? In our case, we are going to use pull up for our input. That way you can just take the input and connect it to any ground anywhere, and it's going to put it down. Make sense?
What's the voltage, minimum voltage?
On this board you have is 3.3. Do not go above. It's going to burn. It can be somewhat tolerant on some FPGAs, but these are not that. I mean, I don't know what. They are not tolerant 5 volt at all. They are not 5 volt tolerant at all. This one. Not at all, at all.
No, they just.
That 2.5 would work because the ref voltage is 1.1, right?
An input of 2.5?
Yeah.
I'm not sure. It has to be like a really good 2.5.
Yeah. I thought the reference voltage was 1.1.
Is it? I don't.
That's something we are not sure because we don't have the schematics of the board.
Yeah, so we don't know what is in any of the power pins.
Yeah. So there is a reference voltage to say what the 1 is, and it's supposed to be 1.1, but we don't know. So you will have to try with 1.8 maybe and see if it switches reliably. And okay, so I told you that registers were kinds of memories. So now we are going to make a register with an arbitrary size. And that's a really cool thing about Verilog and the way you can do designs is that you don't have to care too much about the type of things, where in VHDL you have to be super careful about the types of things and all of that. Here you just say, just want a register that's 200 bits long, and it's going to make a register that's 200 bits long, and that you can address any parts of it or fully and copy it to other registers or to wires and things like that. Does that make sense?
If you don't say reg, what is the size?
Hmm?
If you don't give it a size, what is the default size?
If you don't give a size at all, it's a 1 bit. That's what we did in the LED example. It's just 1 bit.
Okay.
Yeah. There is more than likely a upper limit, but I think it depends on what your design is and all of that. So I have no idea what the upper limit will be on that. It will fail anyway and tell you that it's going to do it. And then there are performance issues because, I mean, it has to wire things together inside the chip. So if you make really long registers, it may have to deal with connecting a lot of modules together that can be far away, so you may have issues with delays when you do really long ones. But again, that's something it's going to warn you about. Okay, so that's the initial begin I was talking about. That's how to set an initial value to a register. You can address your register like you do in most programming languages. So you just put brackets and you can access a specific bit or a specific range of bits inside your register. Oh, this one is failing. So we are going to make two files. Yeah, I'm sorry, this one, I'm going to fix it. We have an update to the LPF file. And I'm going to fix that because that should be on multiple lines. Hmm?
I think you just need 3 ticks.
Yes. Well, and there is no ticks. Yeah, there is no backtick in your LPF file, and each statement should be on a different line.
Oh, I thought you were fixing it.
Yeah, I'm going to fix it.
I
Yeah.
was just saying that.
Okay, so the view graph only applies to these DDR memory interfaces.
Also, it does not for the CMOS.
So
it's 2.
But
Okay.
2 is the minimum for 3.3. So
Ooh, yeah, that's going to be.
yeah, it's if you set it at if you power it at 2.5, then you can go down. to
So what
1.7.
if you put it at LVCMOS 25 when it's not? What is it going to do?
Then I'm pretty sure that as an input, it still needs to clear 2. I think so.
Okay, so where you see
I'll double check.
where you see all these semicolons, you should go to the next line. I think it works if you put it on the same line, but just put them all on different lines. And the website will refresh in a minute or 2.
So in the managing inputs section on this repeat after me
Yes.
part, locate comp port. When I try to run that,
No, that's your LPF file.
okay.
So that's your description of what pin does what.
Okay, so .lpf.
That's the same one you did for the blink.
Oh, okay.
That's what describes what pins do. So you just write it to a new file that you call whatever you want, repeat after me, or something like that. Or call it follow here. So just keep that, follow.lpf, and you put that in that file.
Oh, okay. Thank you.
Okay, so we do something a bit different here. We are same approach as before. We have a top module, we have a LED register, we have a base clock that is divided, but now we have a new module. So instead of assigning the LED to the clock, we are calling a new module, which is called ring buffer. So that's the name of the family of modules, and buffer is the name of the instance of the module. Because that's the thing, if I wanted 200 ring buffers in my design, I could put 200 ring buffers and give them different names. And just have to copy that line and not have to copy that whole block below. And we give it base clock, the port in input, and the output. Okay? And what this does, that's a ring buffer. So that's something that will take an input, put it inside a buffer, and allow you to read it continuously. So when you're done writing, it's going to start again from the beginning and continue writing on it continuously. And same thing when you read, it's going to read continuously inside the buffer. Okay, so what we have here, we have module definition, the buffer size. So here you will see later, but I will make you do it that can be parameterized. So what's going to happen is you make a register that's 256 because the 0 is inclusive. we have a write pointer and a read pointer, which means that you can write at a specific spot and read at a different spot inside your buffer. Make sense? This is super annoying. Okay. Which ones? Sorry.
Like the modules, like a ring buffer. Is that?
So the modules they are, yeah. So it's a design description. So you can use it for FPGAs, for ASICs, for simulations, for anything. It's not dependent on the FPGA at all. Here, the LPF file is dependent on the FPGA because you give the pins and all of that. But in some cases, what you can do in Verilog is that you can instantiate hardware features of your device. And in that case, it's going to be specific for that FPGA. And what you do usually is that you wrap it up in a module that's a normal Verilog module. That way you can change it and just update it super easily. So we are giving an initial value to the buffer. Yeah. So for the ring buffer, you have to imagine. Carl, come here. Come here. What?
Oh no, I just wanted to tell you the input buffers when it's VCCIO is 2.5 or 3.3, it gets powered by VCC aux at 2.5.
Okay.
So you can use.
So it cools. Wow.
You can
okay.
use 2.5.
That's why they do that for the LED.
Yeah.
Okay. So yeah. So stay here is going to be the read pointer, and I'm the write pointer.
Okay.
And this is the ring buffer. So I'm writing stuff, and he's reading stuff in front of me. And once it gets at the end of the ring buffer, it goes back to the beginning, and I go back, and I continue to write. And that's what the ring buffer does. It's continuously writing and continuously. In that case, you cannot. But yes, that's things that could happen. You could read slower and read faster in some cases, and you have to be really careful with what you do. So the FPGAs, they use something which is one step beyond the ring buffers, and that's something really useful, which is a FIFO buffer. So you have first in, first out, and this allows you to cross clock domains. So you are going to store values in it and say, hey, I'm almost full, go take it. And then you can go from low speed to high speed and high speed to low speed communications and make sure they are in sync, and you don't have a clock happening at the same time as the other one and missing everything. So it's just it's a bit abusive to say that, but it's an advanced ring buffer that lets you stop the read pointers until things are ready and go.
How do you, when you're looking at an external line that like a signal can go high or low anytime and you want to read it.
Yes.
How do you get a good solid grab on that so that you don't get a glitch or a metastable?
Well, you use your high clock usually. You always use the highest clock to read the lowest clock signals, ideally.
I'm talking about an unclocked input.
You have to sample it. Whatever happens, you have to sample it. And you have to sample according to a clock. So whatever happens, you will only be able to sample at whatever frequency you have of clock or multiple of it. So you have PLL, so you can generate 900 megahertz clocks if your design can allow it. You could on the chip get 900 megahertz clocks. In practice, you will stay in the 100 megahertz probably with this.
I was reading about using a pair of flip-flops in sequence.
Yes, but then you still need a kind of clock signal to relate to. It's never going to do anything outside of a clock signal, whatever happens. So yeah, if you have a serial thing, it doesn't matter because it's way slower in most of the time than the inside clock of your device, so it doesn't matter. If you have really fast serial systems, then you have, this chip does not have it, but the ones just above do. They have SERDES, which is hardware serializer, deserializer. And they can work at much higher clocks than what you have here. And they can get the stuff inside registers in your device, and you can work with them at much higher frequencies. Okay, so what we are doing here at each positive clock of the positive edge of the clock, we are going to take the data input, put it at the position of the write buffer. Then we are going to increment the write. So that's what we were doing with T. Increment the write pointer, increment the read pointer. And the reason why it works is that because we do this kind of assignments that are going to happen one after the other. Then we take what we say, whatever is at the output of the buffer at the read pointer is going to the output.
The instructor is telling us, is taking us to the next step in the thing and introducing new concepts, and I can't hear it.
Oh, I'm sorry.
Aren't you special?
Okay, so that's what we do here. We take the data in, put it in the buffer at the write pointer, push the write pointer, push the read pointer, and then take the position of the buffer at the read pointer and send that to the output. Yep.
Just wanted to clarify here because this is sequential logic. The stuff on the right-hand side of those assignments are the values before the
Yes.
clock.
Well.
The stuff on the left is shoved in after, correct?
So yeah, that's one of the complicated things about FPGAs. So you have what I was talking about. You have that in the candy jar part of the website. So you have the blocking assignments, which are all going to happen at the same time, and the non-blocking assignments that are going to happen whenever they can. Okay, and it gets a bit hairy the way it works. But what happens at every clock cycle is that the design system is going to make the operation in a specific order, or try to, or tell you that it was not able to achieve that. So it's first going to run all of the blocking statement at once, and then run whatever is on the right-hand side of your assignments, then update the left-hand side, run the continuous assignment, so that's the assign we had for the LED, for example, and then update the input and output. And that it does that cycle that way. So that's why when you do a non-blocking assignment, it takes one clock cycle every time to transmit your value to the next one. Okay? So in that case, it's not always simultaneous. You have to be extremely careful that if you put non-blocking assignment, and if I say B goes to A and A goes to C, if I do a non-blocking assignment, the first clock is going to put B in A, and the second clock is going to put the value you had in A into C. Okay? And this is getting complicated and in the weeds of FPGA design, but
if you go back to your code for a second.
Yes.
I just want to make sure I understood this. So let's say your read pointer is 0, and your write pointer is 0. So then when you're incrementing the read and the write pointers, they're going to become 1.
Yes.
But the buffer that's being written out is 0. So in the 0 space, it's going to be it's going to store data in, and all of this happens at the same time.
So remember that the order of operations, right? We were first doing the blocking. We don't have any here. Then we update right-hand side. Then we update left-hand side. And then we go like that. So we are going to start to put this value here, then increment. And after these blocks, we do the assignment to the output. So at that point, we are already at the next value of the read pointer. But you're right. If you write it with blocking ones, nothing is going to happen because you're going to write and read at the same one.
Okay.
So in that case, the side effect of writing it that way is that they are shifted by 1.
So because these are non-blocking,
yes.
Those 3 things in your always
Yep.
are non-blocking.
Yep.
The state on the right basically gets moved at
Yes.
once, and the state on the left.
Yep. So that's what you need to start to grasp when you work with FPGAs is when are the things happening.
Yeah, in a university class that I took on this, we had to write state machines, and this would constantly be head bang.
And that's kind of what it does when it generates a design. That generates a kind of state machine. That I showed you the steps, and it's going to try to fit these things into that state machine.
So is this four-phase execution sequence like it is true across anything that you do with it? Will you encounter this at any level of anything that you do? Or is this something that you're telling us right now so that we can get a grasp on how the thing goes and we'll learn a larger truth later on?
So that's the thing. Okay, I need to go to that.
In other words, is that a simplified, naive look at it, or is that like really how the thing works under the hood?
Yeah, I'll go to that after. Okay, so the thing with FPGAs is that things happen at the same time, but they don't. So that's
I've never heard this part. I heard
yeah.
things happen at the same time.
They happen at the same time, but they don't exactly. Because you have delays of propagation, because you have these rules that we had from the right-hand side to left-hand side and all of that. So it's not, they mostly happen at the same time, but don't. If you do separate modules that are working on different clocks, all working on the same clocks but not talking to each other, yes, they will run exactly at the same time. If they start talking to each other, then they will have to kind of wait for them, and you will start to have delays building up. Okay? And that's when you need to start thinking about, do I want these things to happen exactly at the same time, at the risk of my value not being ready? Or do I want to make sure that my value is ready before I go to the next step? And that's a choice you have to do when you choose which statement you do. That's what you need to choose. Do I care or not about my data bit being the one I want it to be in that block?
So is there like literally four phases of clocks in there that make these things happen in that order?
It's a design that's going to make that. It's not the device itself. Yeah, yeah.
We're not doing that.
Yeah, but it's a design tool that's going to make that happen. So it's going to make sure that the flip-flops and the lookup tables and all of that are in the right order for this to happen in that order. It's not like a CPU that's going to run instructions one after the other. It's about gates that are going to be ready and send a signal out when the clock is coming and take...
It's almost like if you had a CPU and you had magic and interrupt happened, and two interrupt routines executed at the same time. But one may take a little longer than the other, if they could execute at the same time. They probably don't. Probably different code. So they may start close at the same time, but they're going to finish at the end differently.
But you're not going to get anything faster out of it than the master clock will give you.
No, there's multipliers.
Yeah, you can multiply your clock, so you can make a faster clock from an existing clock, but no, everything is given by a... Even if you use this, it's not going faster than your fastest closed. Just not possible. And things will happen with the clock or around that edge of the clock, but it will happen.
Most of these statements always start with at edge.
Yes.
It's like, we're all going to start at the same time.
It's synchronous logic versus combinational logic.
Right.
Yeah.
Combinational logic, the instant you flip something, something else happens. So if you have an assign, for example, and you flip it instantly, the output is
couldn't get that.
The output of the flip.
That example.
But the on edge, or when you're doing the clock edges, that's combinational logic. So imagine you have a bunch of flip-flops, sequential logic. So you have a bunch of flip-flops that have state, and then on the clock, they're going to flip to the next state.
Okay, so let me just do one quick thing.
Well, yeah. So they're basically what was settled before the clock at the time of the clock is used and then the clock happens, there's going to be some settling time, but then what settles after the clock is going to be what you've programmed. Well, but this is actually a problem, because I've had problems with my own FPGA code, where because of that settling time, it might trigger something else inadvertently if everything isn't going off the same clock.
Okay, so there is one thing you need to be aware of, is that, Ed, you ask for things to happen at the rising edge of the clock.
What happens there?
When you do your designs, you ask things to happen at the positive or negative edge of your clock. So positive edge, negative edge. Things have to be stable before that edge to make sure that your gates or flip-flops or anything are ready to take that signal in. And they have to be stable after that edge as well. Okay? So this is extremely important, and that's where all the timings issue come into an FPGA. So it needs to make sure that whatever was happening before is done by the time you reach that. And it needs to make sure that whatever is happening does not start before that. So now if you have one gate, it looks like that. If you have two of them, you start to at the times of the other one after that. And then the other one, and then the other one. So you have until that time, if you depend on negative edge, you have until that time for things to be done.
So you can get hazards and wedges.
And it will, usually your design tool will tell you, hey, you're asking me for that clock, but I have signals that happen after that clock. So I can only make a clock of 30 megahertz where you ask me for 50.
So you don't have to sit there and stare out wondering where it's coming from. The tool's smart enough to tell you that.
It may still, but yeah, most of the time the design tool will tell you.
That's why he put the LTF file for the clock signal.
Yeah.
No.
Yes.
Okay, this thing's 25 megahertz, and it'll do calculations.
Yeah.
Tools
And if you look into the design tool output, it will tell you, oh, you ask me for that clock, I can do up to that. In the Blink example, it tells you I can do up to 900 megahertz for what you ask me, for example. For the Ethernet one, you ask for 125 megahertz, and it cannot do that. I think it does 90. For these chips, for the Lattice one, you can buy different speeds as well. So you have 3 or 4 speed factors, and this is the slowest one. But if you can buy chips that act faster, and they have shorter times for these. So you can put a lot more things happening in one clock. So it's not just about faster clocks, and be careful, because if you use faster clocks, you have less time for things to happen.
Where's follow LPF?
You have to create it.
I mean,
You create it any way you want.
Refresh your browser, maybe?
Yeah, refresh it. I updated it.
refresh it?
There was a formatting issue, but it's there now.
Yeah, to go back to the programmer's state of mind when you work with FPGAs. So there is this issue of things happen at the same time, but they don't. Loops are completely different than loops when you do programming. When you do programming, it's imperative. You say, make a loop, and this thing is going to happen after that one, and after that one, and all of that. Here, it's not the case. Right? If you do a loop, it will have to unfold it and understand what you are trying to do with that loop. And so in some cases, the design tool is going to understand that and make it the way you want. In many cases, it's not going to do it, or it's going to run everything at once. Because you told it to loop, and it's going to loop, but it's going to loop inside your block. So you told it to iterate, and it will iterate, but it will iterate in that clock time. So you have to think about, what am I telling it to do? Most of the time, if you want operations to happen in sequential order, you're going to make state machines in FPGAs. So you're going to have a register that's going to store where you are in your state machine. And
are those library functions state machines?
no, you make them yourself. Basically, you have a register. And so for basic stuff, you use the integrated scheduling that I was talking about, where right-hand side, left-hand side, and all of that. When you start to have complex operations, you do state machines where you make a register, you set constants to say this 0 is that state, 1 is that state, and all of that. And then you make conditions. I'm in a positive edge of the clock. I'm in that state. if I receive that, I do that. If I receive that, I do that. And that's how you
download like a template for a state machine.
Yeah.
And then you fill it in for
Yeah.
but,
But they are pretty simple. Yeah, the syntax is pretty simple. So you can ask ChatGPT, make me a state machine that's going to work. No, it works. I tried, it works.
Where do you think you would code for all this stuff, Gabe?
Yeah.
He just jumps out the window.
Okay. Don't tell him. Okay.
You told me you coded ChatGPT, so that's
Okay. So did you get that thing running?
Yeah.
So what happened? So what happened? Yeah. What happened when you?
Well, it blinks 3 times fast, blinks 3 times slow, blinks 3 times fast.
Mm-hmm. Okay, so that's the initial, and then what happens? Nothing.
Yeah, and then it turns off.
Okay, so remember we talked about inputs, and we made an LPF file that has an input, and there is a pin that you attributed to that input in your design. So you look on your schematic, you will find the same name for the pin that you did put in your LPF. Yes, that's hard, but that's part of the exercise.
Everybody knows that clock eye.
No, the port I. So it's E1, right?
But there's a definition for clock eye.
Yeah, that's a clock. That's a physical clock that's in here.
Why do we define?
Because we have to tell it when to switch, when it considers that it's a positive edge.
So the logic level for the actual.
We are telling
clock is
it.
inside.
Yeah, we are. No, the clock is outside. It's a resonator outside. Yeah. Okay, so E1. So you find where E1 is. You plug that wire that we gave you in, and then you make it touch anywhere ground on your device. So you can use a USB port, for example, and you make it touch the USB port. Yeah, the HDMI, is it connected to?
Oh, here. But I'm not plugged in.
Yeah, and did it? Yeah, okay.
Do you have the new code running?
Try to do that. Yeah, do it here. Do it here.
There we go.
Yeah, but do it on and off, because you need to see what's really happening. Are you on the right pin?
Yeah, which pin are you on?
Yeah, that looks like it.
This is pin.
Yeah, there is. I mean, you have the full buffer of delay. You have the full buffer of delay.
There's no pin here, right?
Oh, that's Ethernet. Yeah, that's. Yeah. But you were on the right side, right? You were on the right side.
No, I flipped the board around
Yeah.
because to match this.
Oh, okay. Yeah.
Sorry.
That's okay.
That's fine.
So now try it.
So make it. Yeah, do things. Okay.
There you go.
And you see
It's
it
copying
repeat.
here.
Yeah.
Stronger than resistor and like so it looks like we have ground as pin 2.
Okay, you got it?
I'm still having a hard time finding the E1.
Okay. Like that? You know it's not here.
Okay.
You know it's not here and not here because we did not put
you're
the
right, so
pin.
it's gotta be down
So
here.
it's on here.
Ah, there, E1. And so that's the third at the bottom of the pins. Okay.
You got it?
Here.
Like that? You know it's not that one. That can be only that one because that's the only one we gave you already populated, so it's somewhere in here. Yep, there you go. And you can make it touch a ground. I recommend to make it touch here because it's easiest. So you just plug your wire in. And the only thing is just be super careful to not plug it on the 3.3 or 5 volt thing. And make it make it blink. So don't just touch. Make it go on and off, so you can see the ring buffer doing its thing. It's not slow. It's a delay. So it's a delay. It's going to delay by the length of the ring buffer because they are. Yeah.
So like.
How are things looking here?
I got 4 seconds worth of delay. Does that sound about right? Did you ever time it?
Yeah, something like that. You can calculate it. 256 by whatever clock we divide by. Okay. Yes.
Code does not lie.
Okay, so now that you know how to do all that, exercise. You can make it have a longer memory or shorter, or do things faster with the clock or slower with the clock. And the extra thing I wanted to add, the extra thing I wanted to ask for the exercise is try to parameterize it. So look at the clock divider example we have. We have a way to describe parameters. So try to do that with a ring buffer, so you can have a ring buffer you can parameterize. That's the extra exercise. It's harder, but that's.
Then I guess I didn't realize that it starts playing this. It's like this is the buffer.
Well, it's the initial. It's the initial value of the buffer.
Yeah, so the first time that it like plays through the ring, it plays this. But then after it's playing whatever.
At the same time, it's playing it. It's erasing before, or doing whatever input.
Here we start with 0.
It's writing just before the one is reading at.
Okay. Kind of like.
Just wondering something. Why, if there's a pull-up,
Yes.
the buffer is going to be filled with ones.
Yes, but it's.
So
You look.
that's why when I tap this on the USB, I'm grounding it. And then, but then when I ground it, it gets a 0, but then the light lights.
Yes.
So what I'm wondering is what's inverting the LED?
Because the LED is inverted, right?
Okay.
I think that's.
So the LED is hooked up to positive and
Yeah.
Active low.
active flow.
The traditional way to connect LED
whatever we
to a
read,
logic pin was to connect it to the plus.
That's what
And then
Like the next time you go,
Because
so like
Kids can see
now,
more
let's say the wires.
Yeah.
back in the day.
Okay, so therefore
That's what we
a
have.
logic 1
Like this is what I have here is well,
off.
I still
And
have
a logic 0 is
For the LED, just for the LED, not for the real logic.
say like
yes. That makes sense.
It's just how on there.
on the first time around,
Okay.
it's going to be
Okay.
a 1, it's going to turn it on. But then
We had the
also
schematic
plug in
we
the
could show
wire
you,
out,
we
so
don't
it's
have
gonna
the
stay on
schematic.
the
90s.
Oh.
Are you
You
kind of
could
following that?
only
And we just
sync
go
stuff,
around.
but you cannot source.
Okay, that makes sense.
Yeah,
Got it.
TCL Logic
first
is
time
like
that we go around,
400
this
microamps
buffer's gone.
sourcing current.
And it's
and
whatever we
like
shoved
4
in.
milliamps of syncing current,
Yeah,
something like that.
So you
Well, I was
cannot,
following up until
you
that
cannot light a LED with
So,
the original
Reading
TTL.
and writing happens like almost
If
at
you
the
hooked
same
it
time.
to ground.
So like, if
I
these
mean,
were
you
like
could,
clock
but
cycles,
might burn them.
Right.
this,
Very
what I've
dim.
colored in here
That's the.
is the.
I mean, these are really tiny, so maybe they use less, right?
Okay, so this pattern represents.
Less current.
But just obviously hard.
You probably don't need much to
Right,
light
sure,
them up.
But then. Now
I actually have a-
So that's where I'm getting.
This product I'm working on, I have like
So-
a little LED and I don't want it to be too bright and I'm only running like
It's actually doing the reading and
maybe
the.
a few hundred
So like,
microamps
let's
in
just
there.
like stop
Plenty
like one
to-
clock cycle.
to show
Just
you
imagine
that
this
it's
happens.
Yeah.
We can do multiple things. How's it going, Dan?
Hey, Andrew.
So,
I know so you don't help us this year.
yes.
Okay, got it?
So,
I have no idea.
Okay,
I see like,
so where are you stuck? What do you want to do?
Oh, put a block, I want to paste a block comment in here of the next step.
Okay,
Slash, slash,
Yes, that's a line command. If you want to do a block command, that's the same as C++. Yeah, like that.
It is plus plus.
The slash star.
But these are different, like.
Or C, or whatever.
Like that?
Yep.
Well, we're setting this ring differently than when we get all the way around and back to the beginning again. Now whatever new value is here is the new value that it will play. And also read the pin on that same line.
Your coconut.
Not multi-threaded programming.
I understand that the fans are not that great.
Yes.
Well, I mentioned that it's a single-threaded program. You're writing bits into the same. Let's say we have a.
Can't be in here without signing a waiver and I'm
So
sure
like
someone
we have a
find
list of
purposes and whatever else we want.
8 elements.
Yeah, the catch.
We go in the first
You
element.
also signed up for $200.
Yeah.
Yeah. I paid him this one, did you?
Before we go to the next one, we're also going to read.
He takes monopoly money.
pouring through. I forget, it was like some assembly probably support and like
Yeah, I
actually
know,
used a shift
but
register.
it's really bad.
So basically mimic multiple.
So any chance you're involved with IWW or?
No.
I was just wondering, as soon as I heard General Strike, that immediately started thinking about like labor because suddenly it was like,
it was actually 90 days between like, doing the actual math, like just writing it all.
So, well, how does this work, right? This is the buffer, right?
That's not the buffer, that's the initial value of the buffer.
Ah.
The buffer itself is defined here, above.
Fine, And it's 255 or is it 256?
Well, it's 255, it's 0 to 255, so it's 0 inclusive.
This is the range.
Yes. It's a size in bits. Well, yeah, okay, I see what you mean. Yeah, that's a range. Sorry, yeah, never mind. Yeah, that's a range.
The size is that.
Yes, and this is the size.
That's the initialization of it. And that's a write pointer and a read pointer. Buffer. And what is this definition? Ring. Oh, ring buffer is this one.
Yeah, that's the name of the class of the module itself, and buffer is the name of the instance.
Okay.
That's your input wire.
Base clock is just fine in LPF.
No, base clock is generated by the clock divider. So the module just above.
So what is the
A wire is just a way for you to say these two things are connected to each other.
Okay.
So you think of it as a variable, but it's not really a variable because it's not stored anywhere. It's just to tell the design tool these things are connected together.
But what does this tell you? Because it's only one value. What is this connected
So it's not a value. It just tells you.
It's a label on
it's
the
a
wire.
wire. Yeah, it's a label on the wire. It's just.
OR-CAD. You
Yeah.
put the signal D0.
Yeah, it's telling you the output of clock div is connected to the input of ring buffer. That's what it says, without taking any bits in memory or anything.
At different various stages.
Whatever, 200,000. And results in slow clock.
That's how.
So it's the module clock divider with a parameter div of 200,000 as an instance called slow clock.
Oh, instance.
Well, and the instance will have this parameter, not the module. So you could make another divider with a different frequency. You could call it slow clock 2 and.
Well, this is of 2,000. It's for.
Yeah. So if you go down all the way down. That's what's happening. You declare the module, you tell it has a parameter called div with an initial value of that, and then you use it inside as if it was a number. So what's going to happen here, it's not going to change during your program, it's just going to, at the design stage, when you just use the first uses, just going to read that value and replace it. It's not a value you can change during the run of whatever your design is.
Why is it defined? Why is it defined? Like
Here.
It defines it
That's why you define it.
200,000.
Yes.
Well, here it says
Because that's a default value. That's a default value if you don't give one.
But it's not going to use this one. It's going to use this one.
Yes, because you give it one. If you remove that, it's going to use that one.
But is this notation 24?
Same thing as here. That's a size in bits.
24 bits.
Yep.
And this is the value of 24 bits. Okay. And that has a closing code, no closing code. Okay. Weird syntax about. That's a simple injection waiting to happen.
In many cases, you don't need to give sizes because it will guess them. But it's always good to put them because the design tool will tell you, hey, you try to put something as 24 inside the 8, so you're losing precision or you are doing. So it's always good to put them. Okay. So you got the parameters going?
I don't want something to happen. I mean,
link is working. Okay.
Yes.
Yeah.
So the last step is to use the same approach you have in the clock, where you have this parameter called div, to take that approach and use it into the ring buffer. So you can make a ring buffer that you can parameterize the way you want. So try to guess the syntax, how it works, and I know it's hard, but it's on purpose for you to understand why it's written that way and what it means.
I believe you. I just somehow always missed it when.
What's the noun that describes the system uniquely that I couple with that to make a question? Like, what do I call it? It's not FPGA, it's not Verilog,